Okay, we're going to move from two-dimensional data up to a little higher dimension. And one of the first visualizations to try to affect that change in dimension were maps. So we're going to be looking at maps. Maps are actually our oldest data visualization that showed two-dimensional relationships. So for example, here's a 3,500-year-old map of the Sumerian city of Nippur, and you can see various kinds of constructions and presumably roadways and possibly walls, etc. So that's a very, very old map dating to roughly 1500 BCE. So there are lots and lots of old maps. In fact, we can see in 5th century BCE Babylonian world maps. Slightly more speculatively, there have been more recent articles that have been produced by BBC articles from a variety of scientific publications that suggest perhaps that there are in fact 16,500-year-old cave images that show maps of stars or maps of the moon that are 5,000 years old. Of course, today there are tons of sources of maps, particularly Google Maps and Google Earth, with immense amounts of detail, and we have access to all those kinds of sources. And so what we want to look at is, maybe can we use maps to look at how different locations are related to one another? First, just where are these places? Are these places very far from one another? Do they seem to cluster? Are they located nearby? What is the distance? Are there unusual patterns in location? So an advantage of using maps is that they come often with a host of information. So we have lots of information about roads, cities, rivers, lakes, and there's lots and lots of extra information that is immediately available to us. And never before in our history have we had such a great amount of information. So it's generally a good idea to make use of maps where we've got data that are spatially located. So spatial data locations are of two general types, and that's what we're going to be talking about mainly today is location. That is point location, just the exact point value of where is it latitude and longitude, and also polygonal locations, and these are used for islands and lakes and also for political boundaries, somewhat more artificially. So I'll give you an example of very good use of location. Here we have World War II casualties from Toronto, and what you have is every poppy there is a location in the map of Toronto, and every poppy marks a Canadian service person that was killed during the Second World War. And this is an interactive map. You can go and you can look at this location. Patrick Kane, this is a Toronto-based journalist who's produced some interesting infographics. And if you go to that location, you can zoom in and see just where are all of these different casualties located, where are these people that have been killed. So if we zoom in, we could go and click on that and do that dynamically, and I encourage you to do that from the slides in the class, or go to that URL yourself. So if you zoom in, what's remarkable, you have now the detail of roads like St. Clair Avenue here across the middle, and Davenport Road, and we're over here, this is Dufferin Street, and Christie Street here. So we've got this region where there's small neighborhoods, and what's, I guess, really striking is that you see just how dense these deaths are. I mean, there are neighborhoods here that have a huge number, proportionally, especially considering the population of Toronto at the time back in the early 1940s, that have had deaths, in very, very near neighbors, so that these people have been killed in the war. So it really drives home the fact that you've actually got this clustering, that how dense the data are, the locations, and sort of the impact that this must have had on neighborhoods in that time. And we also have that if you hover over these points, you'll pop up and you'll actually see the individual information here. So this is, for example, this is a Robert Cecil Stowe Upton, who was a Lance Sergeant in the Canadian Army and was killed at Dieppe, the first coastal invasion of Europe during the Second World War, the French coast. So Canadians did that invasion, and there was a lot of casualties. That was sort of precursor to the eventual successful D-Day invasion. So what we've got is we can add a lot more dimensionality here. We have these locations, but we can add information on particular people. So we suddenly have got a much richer display. You can see that in lots of different people. So this fellow, Harold Branscombe Hughes, was killed in Hong Kong in 1941 when the Japanese took Hong Kong. And the location itself is, let me just go back, the location itself is what is the most interesting thing, and if it tells a fascinating story if you move over this whole interactive graphic. And again, I encourage you to do that. So that's just plain location with adding some information of just these what are sometimes called tooltips, where you just hover and pop something up. Here's a classic example that is of historical importance, and this is John Snow's map of Golden Square. And what we have is we also have locations that are of interest, locating points on a map. And we have the streets that come with that map here, so we can see Oxford Street and Brewer Street here, and Regent's Quadrant, Regent Street here, so you've got Regent and Oxford Street. And this is the Golden Square area you see down here. And so what we have is every point on this display, every one of these little dots is identifying where there's a death. There's a cholera epidemic outbreak in London in the mid-19th century. And so John Snow was plotting all of these deaths, and you can see that there's a real concentration. So those are the locations that are important, and now it's as with the casualties in the Second World War, you see concentrations in neighborhoods, much greater concentrations here with large numbers of deaths at particular locations, as families and people living together were being wiped out. And at this time, nobody understands what is driving cholera. Snow suspects it's a waterborne disease, but that's not clear to anybody. This is part of his argument. So there are also two different symbols here. So there are these dots that are marking location, but the other location are these X's. And these X's, because Snow believes it to be a waterborne problem, cholera, he has marked all of the public wells where people could draw water to drink. And of interest, of course, is when we zoom in on it, you see on the Broad Street here, there's a pump that's right in the center of this cluster of deaths. And so that's suggestive that perhaps if it is a waterborne disease, which it turns out to be, this could be the cause of much of the deaths. And in fact, Snow spent some time interviewing people at various locations to find out where in fact they got their water from, and indeed most of them, if not all of them, are getting their water from this Broad Street pump. So this is often presented as kind of a smoking gun, that we've got a causal relationship here. And in fact, to assess that, we take Snow takes the handle off the pump, and the number of deaths, of course, declines. There is unfortunately confounding with that, in that also people are leaving the region. If you've got lots of deaths here, people are generally emptying out of London at this time. And point of fact is that this map is actually presented by Snow as part of an argument that is much, much longer in establishing that it's waterborne, including looking at the two major companies that supply water to homes. Many homes had pipes from both companies, and those that drank water from one company were tended to suffer cholera more often than those that drank water from the other company, largely related to where the companies drew their water in from the Thames, whether they're above or below sewage outlets. So this third variant, what we've done by changing the point symbol, either a dot or a cross, so we've added a third variant, just a categorical variant. It's either a well or a death. And that's allowing us to make relationships between the spatial locations and this third variant. Again, noticing the concentration at the Broad Street. And just for the record, here is the Broad Street pump. It's still there on Broad Street, but the handle's still removed. And if you go to London, you probably should go have a visit here. And across the street, you'll see this is in fact the John Snow pub. I encourage you to go and have a brew in recognition of John Snow's great contributions to epidemiology and biostatistical research. Now, one of the problems, of course, with point locations is that these, when we're just putting the points up and we're looking at you know, the third variate here, say our sites users and subscribers to Martha Stewart Living, etc. It may be, in fact, be just like in any statistical analysis, there may be another variant that's actually confounding this. In this case, these patterns look alike, not necessarily because there's a relationship between any of these third variates, but rather there's a lurking variable, this population density. So this is just showing population density. So be very wary of that when you see spatial data and locations, whether you're just reflecting something else, the confounding variable, typically population density. Here is population density, and you can see how that works. Here's a map of the lower 48 United States, and you can see the geography here with Florida down at the bottom and Lake Michigan here, Lake Erie, Lake Ontario. The outline of the coasts, and this is just entirely population from the 2010 census. And what there is a dot aggregated at a spatial level that makes it visible here, a dot for every person in the census. So the census block data, one dot is one person. And what the people have done is the U.S. Census identifies people, or presumably self-identifies people by race, where race here means white, black, Asian, Hispanic, or other. And you can see that this racial distribution roughly has there's an advantage of using color here. I can see this green band here, which suggests that that's a fairly large concentration of people who self-identify as black, and the blue here being large concentration of people self-identify as white. The orange, you can see concentrations, again spatially related, down here at bottom of Texas, that identify as Hispanic. So it's nice that this use of color here, this use of hue, which we've seen as being a bad encoding in when we're just trying to retrieve a single variant. But here, when there actually is a spatial relationship, it does come up with the color as a fine way of distinguishing these patterns when they exist. What's really interesting about this is you can zoom in on the data. So you see the concentration of every one of these little cities where there's a dark patch. People in the valleys here in the Appalachians. And if you zoom in, you get more detail. And now you start to see cities here like Chicago, Detroit, New York, the Washington area. And you start to see a little more color, although the color does seem to be slightly distinguishable from one another. So zooming in even more here on New York, so this is Long Island, that you can see. And to remind you again that there are no boundaries here. This is just the density, population density. So you can actually see Cape Cod and spit out here to Provincetown and Boston as well. And you still see some concentrations of different colors, of the greens and the reds and the blues being concentrated in different areas. So if we zoom in here, this is in the Boston area. So this is Boston, and you can see a large area that is primarily greens, which means this is a large black neighborhood, presumably this around Roxbury and other parts of the greater Boston. In areas that are lots of red, so Asian, largely Asian areas that are orange, where it's a concentration of Hispanic, and it's then concentrations where there are lots of blue. And of course, if you zoom in more, you'll see that there's in fact mixing here. You'll see reds and with the greens and the oranges and blues and reds. So there's a lot of mixing in any of these areas. So lots of blues and reds here and oranges. So it's quite natural that there'd be a concentration here by different racial groups, but there's also a lot of mixing as well. So those are point locations. Another way of looking at location is with polygons, and these kinds of maps are called choropleth maps, which is derived from the Greek for area, region, multitude. And what we have here are polygons. These polygons represent political boundaries in Australia now. And this particular data set, what we're doing is encoding with a single hue, so this greenish hue, going from very light green, yellow to very dark green, encoding in each one of these political regions what the proportion of Anglican Australians are in their 2011 census. So this is a particular Protestant group, originally from England, Church of England, so it's Anglican, Christian faith, and just looking at where there's low proportions of Anglicans and higher proportions on the coasts here. And again, this is the proportion of that population, so we're getting some sense of what that region is like. So we're using color to show the value, and colors will vary with saturation, and you still see some concentration, but you are drawn to looking at these polygons. So the polygons are arguably very unnatural. They're just artificial made because they're political boundaries. Here's perhaps the most famous set of polygons in colors. This is from the United States 2004 presidential election, where George W. Bush was elected, red being Republican, and large amount of discussion about, you know, a red and blue America, with the coasts being all blue, clearly all Democrat, and the Northeast being all blue, all Democrat, and the rest of the country, the middle America here being all red, Republican, and the South and Southeast primarily. So the point is that that's actually pretty misleading. So what we're doing is we're painting a whole area, a whole polygon with one color, is because the aggregation is at the state level, and these are the states went Republican or Democrat, and it gives a distorted image. So it's really distorting the data in the sense of saying there's two kinds of America, all these folks that are all red and the other people that are all blue. And one of the problems, of course, is that this reflects the area. The area of these polygons is what you're seeing. So you're seeing a predominantly red area there. If you look at polygons themselves, it's a little troublesome when you have irregular shapes to determine what is the relative size of these things. So, for example, it may be that, you know, we're looking at areas in which of these four states, in particular Georgia or Florida, which one has the larger area. And given that we're going to color all one color, our eye is attracted mainly to the area and not to the population. So we think about which is larger here, and certainly most people would suggest that Florida is the larger area here than Georgia, and so that may be okay if the population of Florida is that proportionately larger than the population of Georgia. But if it's the other way around, then it's not being very accurate when we're looking at these areas. So you think about that and you say, well, Florida is larger than Georgia. Unfortunately, of course, that's not true. Georgia is about 10,000 square kilometers larger than Florida. So again, this is kind of an optical illusion. Our visual system is suggesting, I'm not sure why, but one can speculate that you're looking at more of the rectangle that defines Florida versus the rectangle that defines Georgia. I'm not sure what, but we generally perceive Florida to be much larger than Georgia when in fact it's not. So even though we're giving it according to the area, it's still, we do not accurately decode that area for irregularly shaped polygons like these arbitrary political boundaries. So back to the distorting the signal. If we make these polygons smaller, so we do this aggregation at a much finer level here, you can see that there's not so much a spatially distributed Republicans versus Democrats, but rather in any one of these regions, and they're small enough, there are red and blue regions. Particularly if we look at the 100% Republican being red, 100% blue being Democrat, and something in between showing the proportion of vote that each of the parties received in the presidential election. It's not really so much a red and blue America as a purple America. And where you're still seeing red and blue is, again, where you're in low population areas that you've got large polygons representing. So it's, again, still misleading. These denser areas, you can see much more overlap, so that there's it's not really that much that particular regions or vast parts of the United States are going one way or the other. So it's a real problem using these polygons. They're generally just a bad idea, particularly if you're trying to use color to in a polygon to convey the magnitude of a third variant. So the other funny thing about the United States electoral system is that it's not just proportion of a vote that you get. In fact, the citizens don't really vote for the president so much as to vote how to tell their electors to vote for the president. Every state has so many electoral college votes, and those and there's a person associated with every one of those electoral college votes, and those electors are supposed to vote then, seeing what the vote is like inside the state for the candidates in the presidency. And some states obligate them to vote in a particular way, and others they have free votes. And it's often, for most states, it's a winner take all. So here is a little better signal of the actual data in the 2012. This is Obama versus Romney, where Obama wins. The blue is now dominating. And what we have here are the electoral college votes. One square corresponds to one vote. So you see this up here for Alaska, it's got 3 electoral college votes, so it's got 3 squares. And Hawaii here has 4 squares. Florida's got 29. So the area now is proportional to the number of votes in the electoral college. And what's distorted is the state itself. So the states are slightly changed, but it's still, you can kind of locate them. So all that really matters is that you can locate the state. You can see the size here. Texas having a large number, 38 of electoral college votes. California is on the west coast still with a huge number, 55 electoral college votes. New York being a big one as well, 29. But you could get a little more honest assessment of the distribution of the votes. Okay, and those are a little more regular. They still are regular, so it's irregular. So it is still kind of hard. For example, looking at Massachusetts here, which they've decided to stick out this spit for Cape Cod, is a little hard to assess that area compared to other areas like that are slightly different shape. You know, New Jersey versus Massachusetts, or somebody. Here we go. Indiana is 11, same as Massachusetts. Massachusetts may look like it's a larger area because it's including this blank spot. So that's the 2012 electoral vote. I thought you might also want to see the most recent U.S. presidential election. So here's the 2016 electoral college vote. And if you look back between these two now, where they're roughly in the same spot, so Clinton is in blue, Trump is in red. And if you look back and see what states changed where Trump won, you're going to see Florida down here, and then Pennsylvania, Ohio, Michigan, Illinois, Wisconsin, Minnesota, not Illinois, Wisconsin and Michigan, in Indiana, Ohio. All of these northern states and the southern state went to Trump, which were not part of the previous Republican seats. The other thing you notice is that some of the electors went rogue. So even though they, so in Washington State here, even though that went for Clinton, 3 of the electors went for different things. 3 of them went for Colin Powell, and I'm not sure whether, I think that may also be in Washington or might be Idaho. One voted for a woman named Faith Spotted Eagle. In green here, somebody in Hawaii went for Sanders. So some of the electors actually went rogue. Other places they actually distribute the vote. I think, for example, in Maine, that's distributing electoral board college. That's not really a rogue vote. So this is maps are kind of dangerous things when you're using polygons. And I encourage you to look at this link, Washington Post. It shows you a lot of. It's a pretty good article talking about how you can tell lies with some maps. So some of the problems with polygons, using those for locations, or with choropleth maps, is that we tend to compare the areas, even when those areas are small. We have trouble ordering shapes by area when they're not regularly shaped. Mixed hues are a very bad choice, because color perception, as we know from first few lectures in this course, that the color perception depends on the neighbors, what we perceive around them. It's also unclear how to match the value that you're trying to encode with the actual perception. We know, for example, by Stevens' power law, that these things for the areas is sublinear, so maybe we should map it into, rather than map the saturation linearly, map it superlinearly so that we perceive it to be linearly, etc. It's also difficult to make comparison between maps. So what might we do instead? Well, the recommendation is that if you can at all avoid it, do not use a 3rd dimension on that polygon in terms of color. Do not use those colors unless that 3rd dimension is actually related to the area. And even then you're in trouble because of the problem with irregular shapes. So the exception of those dimensions that correspond to exact spatial locations, and you want to avoid hue mixes. So you think about if you're looking at, for example, over some particular country's aggression on its neighbors, and it's occupying more and more territory. So you are actually mapping out the change in physical geography. It's maybe not such a bad idea. But if you're trying to map some other 3rd variant, it's not a very good idea. It should be avoided. So what might you do instead? Well, the reason for the polygons is really to actually give you a location. So Dan Carr and some of his colleagues have suggested using these micromaps. And these are, the idea is that you just need these polygons to be simplified so that they're not too complicated, just so that you can recognize where they are. So this is the state of Utah, and it's an example. All that we're using this color for these different regions in Utah, is to identify which region we're talking about. So region 5 is this red, region 4 is orange, region 8 is green, etc. And there's no other measurement that's encoded on here except to look up which region is which. So it's easy to find where is it on a map. Now, what's suggested is that you put the statistical data in a proper statistical graphic. And so what you would order, you have some measurement here, say percent of some variant, and you order the regions by one of these variants. So in this case, looks like it's ordered by the statistical panel 2, from the smallest to the largest, broken into 2 pieces, those that are on the top half and the bottom half of this particular value, so that we can see, imagine moving from through these colors of the rainbow here, red, orange, green, blue, violet, are those associated with any sort of spatial representation. Also, you can have other variants here. So these are, another variant in this first panel, another variant in this 3rd panel, and see is there a relationship between these other variants and the variant of interest and the spatial locations. So whatever this variant is, it looks like the southwest part of Utah is most associated with the low values, and the northeast part is associated with the higher values. So again, these are just to have as a lookup, and this become a little more obvious what the value of this is when we look at some real data. So Dan has also published some data here on mortality rates, cancer mortality rates for white males in the north. Looks like, well, not quite the northeast. It's northern part of the Midwest states, and you can recognize roughly there's Lake Michigan there, Lake Huron, Superior. You can see our border. So that looking at these states are ordered by their age-adjusted cancer rate. So deaths per 100,000, from the lowest number of deaths per 100,000 to the highest number. So the highest number is Indiana, and the lowest number being North Dakota. And you wonder, okay, as we move this way, is there any spatial relationship? It kind of looks like going that the number of deaths per 100,000 for white males for all types of cancer seem to be going from the northwest to the southeast in this region. The band there, the band there, band there. The other thing it's done is, whereas moving from top down, any state that's appeared above is shown in a light yellow, so that by the end we can see that everything has appeared above. And these are the middle states, and they're actually middle states spatially as well. So again, the color patch is used only to identify the location, and this scatter plot here is used for the third dimension. You can have more complex things here. So now we're looking at poverty and education in the southern U.S. states in 2000. So the percentage, these are ordered by the percentage below the poverty level. So low percent is good, high percent is bad. And we order all of these, again, with panels that have just a small number of colors. So we only have 4 colors in each one of these panels. We have an odd number here, so there's actually a median. The median poverty level in this group of states, which, as you can see, is mostly the southeast. It's the middle state is Oklahoma. So, and the best state here is Maryland, and the better states seem to be up here in this northeast block up here. The lowest are down here, Mississippi and Louisiana, West Virginia, and DC. So DC is a bit of a problem here. We're looking at connection between poverty level and then the proportion of adults, or rather the percent of adults in that state that have at least 4 years of college education, so post-secondary education. And you see that it does seem to be that the lower poverty levels seem to be associated with higher levels of education, with the exception of Washington, D.C. So that's kind of interesting. You might think about that one. Really stands out, that it has very high levels of education. Nearly 40% of the adults have 4 or more years of college education, yet they have the the highest poverty level. So that's a very different from the rest of it. And you might think about why that is, that there's the quite probably income disparity that's in Washington, D.C. itself, but also there's a bit of an unfair comparison here because D.C., this is a city, and these others are states, so there's a lot more that's spread out across the state. If, for example, you took the major city of every one of these states, it might tell us a slightly different story, and that Washington might not look as bad as it does, or it might, yeah, but that would be interesting to compare with other states, with other major cities in each of these states. But that adds another dimension, and the number of colors is kept very simple. They're entirely, again, just for lookup. So continuing with interesting data sets here using micromaps, Now we're looking at over all of these states and Washington, D.C. with the same data. So the least poverty is in New Hampshire, and the highest is again Washington, D.C. Again, a bit of an unfair comparison because that is a city as opposed to a much bigger geographic region. You know, perhaps it's comparable to Rhode Island. There's a bit of a fair comparison to a small state like that, but not so much for Texas or California or other large states. So, for the most part, you see that there is a relationship that the number of adults with 4+ years of college does seem to be increasing as we're moving up here, and that's associated with moving up is decreasing poverty level. Again, the exception here being the Washington, D.C. Now Wyoming's the median. And we see again the colors up here, just look up the northeast here, and now the advantage of having the yellow is you can kind of see, well, who's still above here, above the median, what part of the country above the median in terms of low poverty levels and high poverty levels. Now it's a shame. Sometimes you would have actually this all be white here and yellow's just showing what appears, so you can have the other direction as well. So the same as this, but in the other direction. Because right now you just see that everybody above here has less poverty. So here's the case in point. This is exactly what I was just saying. This is the same thing here, but now we see that as we're collecting yellow states, we're just collecting those that are above, and same here, these are just the guys that are below. This is a much better indication of where already here, where the high poverty is, and that's these bottom states here, and where the low poverty is, these top states. You see a division with this little group here. So again, the other thing that's added here is a smooth. So we could run a smooth through all of this data, give a better sense of where that average is, and also looking at the residuals here from the smooth. So you immediately see long horizontal lines with the guys that are perhaps not following that trend throughout. So there's for the number of people that are below the poverty line, there's a large number of people in Massachusetts that have 4+ years of college, and same with Colorado, but still have for that group, fairly high poverty. The statistical graphic can be anything. So here we're looking at showing some change over time. So what we have now is a time series, and we again got the states divided, these cumulative micromaps where we're having the highest rates at the top here and the lowest rates at the bottom. This is primary syphilis in males from 84 to 2003. Again, Pearl District of Columbia is at the top, but probably a bit of an unfair comparison, again, because it's a city. And you can see other areas here. And the more you know about it, you think, well, I wonder why that is, that Nevada, Louisiana, Florida might have high syphilis rates. And the cases per million for the time series for Washington, D.C., you can see this remarkable sharp peak up to 1,200 cases per million males having primary syphilis, and that was around 1990. And so you can see the whole time series. Do they look alike? And the colors to allow you to look at which regions. And again, the south here, around in southern Mississippi, where we're having high rates, and here in the New York, California, New York, entering Texas. So it's interesting to see where are these rates high and where are they low. The other indication that's being used here is color as the background. So if this graph has the same background color, this is one scale from 0 to 1,200. These gray scales with the gray backgrounds are all from 0 to 360 cases per million, and the bottom ones are again, roughly a quarter of what it is before. So these peaks here are about a quarter of what they might be in any of these panels, and they all have the same thing from 0 to 80. So nice use of micromaps here so that I can see the statistical data. I can look up Also see, is there a concentration of the spatially of these high areas. So another way of showing change, looking here at migration patterns. This here, this state of interest is Iowa, and we're looking at people that move to Iowa and people that move from Iowa, where they move to and from. So if we're looking at Iowa welcomes, we see arrows connecting the states. So the green state here being California going to Iowa, and the people that are the largest group of numbers that are moving to Iowa are, not surprisingly, the neighboring states and California. Now, where people from Iowa are moving to, again, not surprising, the neighboring states, but this time Texas they're moving to as being the highest value. So these are two sets of micromaps side by side, and what we're showing is the flow into Iowa. Again, light green showing the cumulative states that have already appeared. Seeing the light green flow, the flow into Iowa in this column, and the flow out of Iowa in this column. So you get to see these little edges connecting the states, so that it's a little easier to emphasize that we're looking at the change from Iowa to the other states. And it's of interest to see how different these are from one another. Already the difference we noticed between Texas and California, also Florida there. So that's showing some flow. So that again